Today in this lecture we will discuss about introduction to electronic properties, free electron theory and Fermi energy. So let us start from introduction to electronic properties. Now first let us see some basic terminology related to electrical conductivity. First, Ohm's law. It states that the current through a conductor between two points is directly proportional to the voltage across two points. So this is a voltage across these 2 points. The current is flowing through this conductor, that is I, and R is a resistance. So the equation is I is equal to V by R, means V is equal to IR. So this is a Ohm's law. Now resistance denoted by capital R. It is the opposition that a material offers to the flow of electric current. So this is our conductor. Rho is a resistivity. Okay, A is a cross section area of the conductor and L is the length of conductor. So capital R denotes the resistance. So factors on which the resistance depends. The first is length of wire, or you can say conductor, cross sectional area of wire conductor, nature or type of material, and last, temperature. So resistance increases with increase in temperature. So R is directly proportional to L by A, where L is length of conductor and A is cross section area of the wire or conductor. So if we remove this proportionality, R is equal to rho L by A, where rho is a proportionality constant, that is called resistivity, or R is equal to L by sigma A, where sigma is equal to 1 by rho, called conductivity. So unit of resistance is ohm, unit of resistivity ohm meter, and unit of conductivity mho meter inverse. Now current, the flow of electric charge is called current. So current denoted by I is equal to Q by T, coulombs per second. Unit of current is ampere. 1 ampere current represents 1 coulomb of electric charge, that is 6.24 into 10 raised to 18 charge carriers moving past a point in 1 second. Current density J. It is defined as the current per unit area of cross section of an imaginary plane held normal to the direction of flow of current in a current carrying conductor. So J is equal to I by A, and unit of current density, that is ampere divided by meter square. Electric field E. Potential gradient is defined as the drop of potential per unit length of conductor. Electric field is the negative gradient of scalar potential. Negative sign denotes that work is done per unit charge. So we can also define that electric field is a potential drop per unit length of conductor. That is E is equal to V by L, and unit of electric field is volt per meter. Electrical conductivity sigma. It is the measure of amount of electric current a material can carry on its ability to carry electric current. Now we know that Ohm's law V is equal to IR, but R is equal to L by sigma A. So V is equal to IL by sigma A. Here I by A is equal to V into sigma by L. But we know that I by A is equal to J and V by L is equal to capital E. So J is equal to E into sigma, or you can say sigma is equal to J by capital E. So it can also be defined as rate of charge flow across a unit area per unit potential gradient within a conductor. So the unit is per mho per meter. Next topic is free electron theory. So electron theory of metals, in which the study of valence electron present in band which controls the various properties of metal is called the electron theory of metals. So this is a nucleus and these are the valence electron. It is classified into three types: classical free electron theory, quantum free electron theory, and band theory of solids or John theory. So in classical free electron theory, it is also called the Drude-Lorentz theory. They tried to apply the features of kinetic theory of gases to derive Ohm's law. Quantum free electron theory. This is also called Sommerfeld theory. He tried to remove the drawbacks of classical theory by applying quantum theory. Band theory of solids or John theory, which is developed by Bloch. Classical free electron theory. This was developed by Drude and Lorentz. In this theory, the free electrons in a metal are treated like molecules in a gas and Maxwell-Boltzmann statistics is applied. Maxwell-Boltzmann statistics describes the average distribution of non-interfacing material particles over various energy states in thermal equilibrium. It is applicable when temperature is high enough to practice density is low enough to render quantum effects negligible. So the function of E is equal to 1 by A into E exponential raised to capital E by KB into T, where Fe means function of E, that is probability that a particle will have energy E. A is equal to normalization constant and small e, probability for occupying a given state decreases exponentially with time. Main assumptions for postulates of classical free electron theory. A solid metal has a nucleus positive with removing electrons, that is negative. These electrons move freely like molecules in a gas. The free electrons move a uniform potential field due to ions fixed in the lattice. In the absence of electric field, means capital E is equal to 0 in this case, free electrons move in random directions and collide with each other. During these collisions, no loss of energy is observed as the collisions are elastic. So here when electric field is applied, E is not equal to 0. The free electrons are accelerated in a direction opposite to the applied field. So when we applied the field here, the electrons moves opposite direction. As the electrons are assumed to be gas, they obey laws of classical theory of gases. Free electrons obey Maxwell-Boltzmann statistics. Now, success of free electron theory, it verifies Ohm's law. It explains the thermal and electrical conductivities of a metal. It helps to deduce Wiedenham-Franz law. It explains optical properties of metals. Drawbacks of classical free electron theory. The theoretical value of specific heat and specific heat of metals obtained by this theory is not in agreement. With the help of theory, electrical conductivity of semiconductors and insulators cannot be explained. The theoretical value of paramagnetic susceptibility is greater than experimental value. Ferromagnetism cannot be explained. At low temperatures, electrical conductivity and thermal conductivity vary in different ways. So, K by sigma T is not a constant, but according to classical free electron theory, it is a constant at all the temperatures. The phenomena such as photoelectric effect, Compton effect, and black body radiation cannot be explained by this theory. Now let us see Fermi energy. So Fermi level and Fermi function. Fermi level means the highest energy level which an electron can occupy at absolute zero temperature is called Fermi level. And Fermi energy, the energy possessed by electrons in the Fermi level at absolute zero is called Fermi energy. So here we have uh, three different types of materials like conductor material, semiconductor material and insulator, in which this dotted line is known as Fermi level. So Fermi level is overlapping in conductors, and there is a gap between conduction band and valence band in semiconductors and insulators. So for conductors, Fermi level is inside the conduction band, and for semiconductors and insulator it is in between conduction and valence band. Now Fermi function, also called the Fermi distribution function. It gives the probability of occupancy of energy levels by fermions in terms of Fermi energy, temperature and Boltzmann constant. Consider a system of electrons in thermal equilibrium at temperature T in Kelvin. The probability Fe, this is a function of E, of an electron occupying any particular energy level is given by this equation, where F function of E is equal to 1 by 1 plus e raised to E minus Ef by Kb into T, where function of E is equal to Fermi function, E suffix F is equal to Fermi energy, T is absolute temperature, K suffix B is Boltzmann constant, which is always 1.38 into 10 raised to minus 23 joule per Kelvin. And from the above equation, we can say that a system is characterized by its temperature and Fermi energy EF. For a filled energy level, probability is equal to 1, and for unfilled level, probability is equal to 0. Means the function of E 1 and function of E is equal to 0. The dependence of Fermi function under different conditions of temperature and energy level is EF. So case 1, at T is equal to 0 means absolute 0 temperature, where energy is less than Fermi energy. So at absolute 0, electrons occupy the lowest energy level first, followed by next higher level as per Pauli's exclusion principle, that is 2 electrons with opposite spin per energy level. Now first at T is equal to 0 Kelvin, where energy E is less than EF, means energy is less than Fermi energy. For energy level C lying below EF, so this is a graph in which energy versus distance, EF is Fermi energy. So E minus EF takes negative value. Okay, the function of E is equal to 1 by 1 plus e raised to E minus EF by Kb into T. So if you put the value of E that is less than EF, okay, so this value is negative, and the whole E minus EF by Kb into T, where T is equal to 0, so negative by 0, that is negative infinite. So the function of E is equal to 1 by 1 plus e raised to minus infinite, and e raised to minus infinite is equal to 0. So 1 divided by 1 plus 0 is equal to 1. So here function of E is equal to 1. This implies that all energy levels below EF are completely filled. So below this level EF, okay, the energy level is filled. Now B case, at T is equal to 0 Kelvin for E greater than EF. Here the value of E is greater than the Fermi level. So for energy level E lying above EF, and E minus EF takes a positive value. So if you put here positive value, our value of this E minus EF by KB into 2 will give the only infinite. So E raised to infinite is equal to infinite. So 1 divided by 1 plus e raised to infinite is equal to 1 by 1 plus infinite is equal to 1 by infinite, and is equal to 0. So the function of E is equal to 0. This implies that all energy levels above EF are completely vacant. So there is no possibility of electron occupying an energy level above EF. So above EF there is no energy level. Only below EF there is a energy level. So verification of function of E at T is equal to 0 Kelvin. So the variation of function of E at T is equal to 0 Kelvin for different energy values of E takes a step as shown in above figure. Case number 2, at T greater than 0 Kelvin means something about the room temperature. So at room temperature, the probability starts reducing from 1 for values of E close to EF but larger than EF. Okay. So at T greater than 0 Kelvin for E is equal to EF, the argument in the exponential function becomes 0. So your function of E is equal to 1 by 1 plus e raised to E minus EF. When you put E is equal to EF, this value become 1. Okay, so 1 by 0, that is 0. So 1 by 1 plus e raised to 0 is equal to 1 by 1 plus 1, and 1 half means 0.5, where e raised to 0 is equal to 1. So function of E is equal to 0.5 implies that probability of occupancy of an electron is 50% at any temperature above 0 Kelvin. So for E is equal to EF, the value of function of E falls off to 0 rapidly as shown in figure. When E is equal to EF, the energy level goes down. Okay. So from 100% probability, we know that a function of E is equal to 0.5. So there is a chance of 50% filled and 50% empty of energy level. Case 3, when temperature is very high. So at very high temperatures, it can be seen from the below figure that the transition between completely filled states and completely empty states is rather gradual than abrupt. So Fe changes from 1 to 0 more gradually. At temperature T increases, electron may get an energy of an order kb into T and go to the higher vacant state. As a result of this, the Fermi function falls for the energy below EF such that E minus EF is always greater than kb into T. The value of Fe will be unity. Okay. So function of E begins to fall. So here you can say this is a probability when E is equal to EF, okay, 50% probability. And when you increase the temperatures for T is equal to 300 Kelvin means at room temperature, this is our graph, okay, from here to here. But when temperature is 1500 Kelvin, it falls from here to here, okay. And at high temperature 2500 Kelvin, it will be like this. Okay, thank you very much for watching this video.